Hi guys, in this video we're going to take a look at an interesting reaction called the Aldol reaction. Essentially it's a reaction of aldehydes or ketones. And in this particular example we'll look at two ketones reacting, or two the same ketone reacting, due to a compound called a beta-hydroxycarbonyl. So this could be, in effect, two aldehydes. It could even be an aldehyde and a ketone, as we'll see a little bit later on. So let's have a look at how this reaction occurs, and we're going to have a look at propanone. And the key thing about propanone is that the hydrogens bonded to the alpha carbon, and the alpha carbon is the carbon next door to this carbonyl carbon. These hydrogens are acidic, which means they're lost relatively easily. And we need to explain why these hydrogens are acidic. So these hydrogens here bonded to the alpha carbon, these hydrogens are acidic. So let's have a look at why they're acidic. Well, sodium hydroxide, and again when we're looking at sodium hydroxide, which is what we need for this reaction, we never include the sodium in the mechanism. So these hydroxide ions then act as a base, a hydrogen ion acceptor, and pull off one of these acidic hydrogens. And the pair of electrons, we're just going to say, are going to then go to this carbon. So then we've got to draw what the consequence of those curly arrows are. So what we can see is that we've pulled off this hydrogen. In effect, this lone pair here is forming a new oxygen-hydrogen bond, of kind of forming water, if you like. So we can break this bond. And the pair of electrons that were in this bond are now going to belong to this carbon. But this negative charge can be delocalized, and we can show that by, again, looking at some curly arrows. So we can see by drawing these curly arrows that we can move this negative charge onto this oxygen. So if we draw, again, the consequence of those curly arrows, so we can see here that the pair of electrons there are now being used to form this carbon-carbon double bond. So let's draw my carbon-carbon double bond. And the pair of electrons that were in this carbon-oxygen pi bond, these pair of electrons have moved and are now owned by the oxygen. So we need to break this pi bond, and the lone pair now is on the oxygen. So we've got these now, these canonical forms, these resonance structures. And obviously this means that that negative ion is a bit more stable because the negative ion is not fixed on one atom. So remember that resonance is the idea of the delocalization of pi electrons. So these here are the pi electrons, and instead of being fixed between these two carbons or fixed between this carbon and oxygen, then pi electrons are actually spread over the two carbons and the carbon and the oxygen. So it's kind of half a bond there and half a bond there, and the negative charge is kind of, you can think of on average somewhere in between. And again, anything where charge can be spread is going to make that species more stable. So what happens next is this negative ion which has been formed here, this now can act as a nucleophile and attack another propanone molecule. So let's draw another propanone molecule. Let's just copy this one, for example. So this propanone molecule now can be attacked by this nucleophile, and let's show how that occurs. Just kind of get rid of these highlighted hydrogens. So what happens now, and I'm going to show it with this particular one here. What can happen now is that we can reform the double bond. And in doing so now, this carbon here has too many bonds, so this bond's got to break. And the pair of electrons here can now be used to form a new carbon-carbon bond. And as that bond starts to form, we should be aware now that that bond is going to break. And we're going to look at what the product formed is. Now, I think when we're doing stuff like this, it's easy then to just count my carbons. So I'm going to call this carbon 1, carbon 2, carbon 3. And we'll call this carbon, say, 4, carbon 5, and carbon 6. So in effect, we're forming a new bond between carbon 6 and carbon 2. So remember, it's always going to be this carbon it's going to form the bond with. So the resulting product then would look like this. And we'll just kind of, hopefully you can try and, again, if you want to try and pause the video and figure out what the structure is, that's absolutely fine. And see if it matches the one that I come up with. So what we've got then is this compound here, which I've kind of copied. And again, we should realise now that we've got a negative charge and this lone pair here. We've now formed a new bond between carbon 6 and carbon 2. So the new bond which is being formed, and I will do this in green, the new bond which is being formed is this one. That's my new carbon-carbon bond which is being formed. And it's being formed there between carbon 6. So let's label this carbon 6. Then we've got to think about what is bonded to carbon 6. Well, bonded to carbon 6 is 2 hydrogens, first and foremost. So let's draw them. So you can see there, carbon 6, 2 hydrogens here. And then we've got carbon 5. So let's draw carbon 5. Label it carbon 5. And carbon 5 now, we should see, has got a reformed carbon-oxygen double bond, because the pair of electrons there reforming the double bond. So I've got a new sort of reformed carbon-oxygen double bond. And bond to carbon 5, we've got a CH3 group. And that carbon there we called carbon 4. So that's the product which is formed. And then what happens next, this is essentially a nucleophilic addition mechanism. What happens next is that the oxygen with a negative charge then gains a hydrogen. That in effect is going to form an alcohol. So we'll just have a look at the structure of the product formed. Well, let's just copy this out. And hopefully it'll fit on. Well, we may have to just put it down a little bit further. So what we get then is we've obviously used this lone pair here to form a new OH bond. And that there is my product, which again, if you look, is what we have here. It's exactly the same. And let's see if we can name this. Let's get rid of these numbers. So again, in green was my new carbon-carbon bond that I formed. And let's number these then. So I would always number from this end now, 1, 2, 3, 4, and either of these two here could be 5. It doesn't matter, we'll just pick this one. And what we've got then is we've got my longest carbon chain has been 5, so it's going to be pent. We've got a ketone group coming off carbon 2, so it's pentan 2-one. And hopefully you can see we've got a methyl coming off carbon 4 and a OH is a hydroxy coming off carbon 4. So this would be 4 hydroxy and 4 methyl pentan 2-one. Let's move this across. So that will be the name of this compound, and that there's a beta hydroxycarbonyl. Why would we call it a beta hydroxycarbonyl? This here is my alpha carbon, and this here is my beta carbon. Obviously, we've got a carbonyl here, and we've got a hydroxy group, which is on the beta carbon. So this is why it's called a beta hydroxycarbonyl. Now, this reaction occurs in biological systems, and it's a reaction called gluconeogenesis, which I'll just move this up a little bit. What we've got here is we've got a ketone. Initially, we've got a ketone here. This is called dihydroxyacetone phosphate, and an aldehyde, which is glyceraldehyde 3-phosphate. And gluconeogenesis is the process where our bodies make new glucose, hence the name gluconeogenesis, making new glucose. And it makes it by combining these 2 3-carbon sugars here into a 6-carbon sugar. Now, in this particular reaction, the acidic hydrogen which is removed is this hydrogen here. So that's my acidic hydrogen. And it's going to attack this carbon here. So we form this negatively charged species. So if we think about what we're going to get then, we remove this here, and in effect what we're then going to get is, oops, sorry, put it in black. We get this and if we follow this through, this then will attack and do something like this. So what you're going to get then is a new carbon-carbon bond formed. And the carbon-carbon bond, let's see if we just number this. So if we number this, say 1, 2, 3, 4, 5, 6. We're going to get a new bond between carbons 1 and carbon 4. So again, what would probably be a good idea is if you kind of pause the video and see if you can figure out what the structure of the products would be. So let's have a look at and see what our product would be. The product formed is actually going to be something called fructose 1,6-bisphosphate. So what we're going to have then is I've got carbon 1, carbon 2 and carbon 3. And let's fill in. So I've got an OH on here, nothing's changed. I'll just move this arrow over. Nothing's changed there. We've got this OH. We've got a hydrogen. And carbon 1 now, my new, and I'll draw this in green, we've got a new bond between carbons 1 and 6. So this is carbon 1, 2 and 3. Let's just fill the rest of this in. So carbon 2 has got a now reformed double bond oxygen. And carbon 3 has got 2 hydrogens. I'll put these numbers back in a sec. 2 hydrogens and this phosphate group. So what we've got now then is carbon 4. I'll just put the numbers back in. carbon 2, carbon 3. So we've got carbon 4 there, and attached to carbon 4 now is the hydrogen. Now got an oxygen with a negative and a lone pair, and we've got, in effect now, this is carbon 5. And carbon 6. So attached to carbon 5, we had an OH and a H. So you've got an OH there and a H. This is carbon 4, carbon 5, carbon 6. Attached to carbon 6, we had 2 H's and a phosphate. So again, let's draw them in. So I'm trying to show you how you can sort of figure out the structure of a product as well. So that's what we've got. And then obviously what occurs next is that we gain a hydrogen. And that in effect forms an alcohol. So I'm going to just be a bit naughty and put that OH in. Then that's actually my final product. That is fructose 1,6 bisphosphate. And you can see that it's still a beta hydroxy carbonyl. If that's my carbonyl carbon, again, that's my alpha. And I have got this hydroxy group on the beta carbon. So that is fructose 1,6 bisphosphate. And that's an example of an aldol reaction in biological systems, an example of how we use an aldol reaction to form carbon-carbon bonds. So that is an important reaction. The aldol reaction occurs with aldehydes and ketones. In essence, it's a nucleophilic addition mechanism and the primary way in which our bodies will make new carbon-carbon bonds.